Okay, you know the story now. We are slowly building towards adding more and more of the MJO structures and trying to discuss the processes that explain them. So we looked at frictional convergence, wave cisc, evaporative heating, and so on, and argued that frictional convergence so far has been needed to explain many of the features, but there are still some features left, and they come out of something called multiscale interaction, and a model is built for this kind of explanation of other features as well. So let's start with this figure, which is showing the larger scale MJO envelope that we talked about, with convergence in the lower level, divergence in the upper level. And if you know what a Gill heating structure means, Adrian Gill had done some seminal experiments where he showed that heating in the troposphere would produce this quadrupole structure in vertices at the surface level and the upper level, which became kind of a classic for the tropical circulation problems, which then could combine waves and mean flow and various other things we've been talking about, including moving the heating during El Nino periods and so on. Here we are looking then at the supercloud clusters that we mentioned, which propagate eastward along with the MJO but are tilting backward with respect to their propagation direction, and they are typically in the back side of the MJO as shown here in the westerly phase, and they are able to transfer that westerly momentum to the upper layer through eddy momentum transfer. And you have the two-day waves, or the westward inertial gravity waves, which are in the front end of the MJO typically from observations, and are tilting forward and are in the easterly wind anomalies associated with the MJOs, and are the eddy momentum transport here is of the easterlies upward. So the schematic diagram is basically describing the multiscale structure and interaction associated with the model MJO, which we are dealing with here. The solid ellipse and the short thin arrows denote vertically tilted synoptic disturbances. So SES is in the rear and the two-day waves in the front of the MJO convection center, and associated convergence and divergences respectively, obviously. The long dashed arrows represent eddy-induced upscale easterly and westerly momentum transfers. Okay, so there is the long dashed arrows somewhere, which you can find here, for example. The convective complex and the planetary scale zonal circulation associated with the MJOs are included here as well, with the thick arrows. The long thin arrow represents the boundary layer Ekman pumping here, or the BLEP, boundary layer Ekman pumping. So in a simple case, this is a heating, and you have the westerly momentum transport and easterly momentum transport happening here, and we will come back to this in a little bit. But taking all these processes, a model is built for this multiscale multiscale interaction model, which obviously I'm not going to explain all of these terms, but I will show a table which talks about the processes that for which coefficients are assumed. So these are non-dimensional coefficients C1, C2, C3, C1, C2, C3. They denote respectively the magnitudes of eddy momentum transfer, boundary layer moisture convergence, and lower free tropospheric moisture convergence. Looking at the table of MSI model parameters for wave number 1, which is the solution we will look at, when you make it more complex, you will get other features that are not explained here in the next couple of slides. So you have the beta parameter, gravity wave speed, which is considered here as the gravest baroclinic mode. Momentum and heat damping, Ekman damping, spatial lag between stratiform and deep convective heating. So you have now heating that is much more complicated than the three we saw before. And we also consider the ratio of deep convective heating to total, so stratiform and cumulus congestus heating, for example, to the deep convective heating cumulonimbus. Dimensional amplitude of the eddy momentum transfer, depth of the boundary layer, what else is special? The constant associated with EMT, and so on. So it's obviously much more of a complicated model. You look at the results in terms of alpha, which is the ratio of deep convective versus total condensation heating. So deep convective versus deep convective plus stratiform plus cumulus congestus heating, which gives you the sense of the MJO related heating versus the larger scale convective complex condensational heating. So you look at the growth rate and the phase speeds for the range of alphas when the ratio is 1. So the convective heating is basically determining the total condensation heating. Then you have the multiscale interaction that is with frictional convergence instability that is dropping off as the ratio decreases. So the convective heating is dropping and the stratiform and congestus are increasing relative to the convective heating. Then the frictional convergence growth rate drops, as you can expect, because you get more and more into the linear kind of heating range that we talked about before. So you will get just some of the features and not the expected growth rates. Frictional, so the eddy momentum transfer itself begins to dominate when the convective heating becomes almost equal to so you are going here from 1 to 0.5. So at 0.5 the deep convective heating and the total condensation deep convective heating is half of the total condensation heating, so 1 divided by 2. So you have the EMT dominating at that point, but you can see that the multiscale interaction, which is a combination of frictional convergence instability and the eddy momentum transfer, can generate required growth rates at all ratios of alpha. So this says that you cannot explain everything just with eddy momentum transfer or frictional convergence instability. The multiscale interaction is important to get the growth rates to maintain the instability, because here you begin to get a damped. So once you growth rate goes negative, obviously you are in the damped mode and the instability doesn't grow. So the EMT by itself doesn't kick into the unstable mode till you cross alpha of about 0.65 or so, okay, and then it begins to become equal to the MSI at the ratio of 0.5, but here other features like propagation cannot be explained. So that's why you look at the phase speed here, for example. So there is the MSI, which the phase speed drops below 10 meter per second once you cross the alpha of 0.7, whereas FCI by itself is not able to explain the slower phase speeds of the MJOs, so it's too high here at close to 30 meter per second, whereas EMT by itself is very high when alpha is 1, and then quickly drops off to 0, and then it doesn't propagate, just becomes stationary when alpha is dropping below about 0.85 or so. So the main message is that growth rates and the propagation speeds together are best explained in the range by the MSI as a combination of FCI and EMT. If you look at the horizontal structures of the three unstable modes arising from frictional convergence, instability, eddy momentum transport, and the multiscale interaction and their movements along the equator here in D, the structures were made here for alpha equals to 0.6 and at day 7 and shown by planetary scale winds which are shown as vectors, and areas of convective heating which are in the deep thick contours here. Okay, what else? Thick contours, as well as streamlines which are the thin contours. The vectors and convective heating contours are scaled to their respective maximum amplitudes, so 1.5 meter per second, 0.2 Kelvin per day, 3.7 meter per second, 0.45 Kelvin per day, so heating rates and propagation speeds. 4 meter per second, 0.6 Kelvin per day. The movements are shown by the time longitude diagram of the simulated core heating associated with the FCI, EMT, and MSI modes. Okay, contour intervals, etc. So essentially, you are looking for the quadrupole structure again, and you can see which one dominates the Kelvin wave structure versus the Rossby wave structure. Depends on which mode dominates. So the FCI, EMT, or the MSI, and the in terms of the longitudinal propagation as well, you can see where FCI going too fast, EMT becoming stationary, and MSI giving you the right kind of speed. And the structures are also better explained by the MSI instead of just FCI or EMT. Okay, so it's kind of a post facto justification, but one should remember that in these idealized cases there are assumptions made about the structures. For example, the one mode, baroclinic mode represented here, allows you to understand the processes, but obviously the reality is much more complex. That you need the multimode structure to capture the more realistic features of MJO in terms of the eastward propagation, the tiltings, the supercloud clusters, the two-day waves, the convective complex, and the lower and upper layer structures. So that kind of begins to tell you how we add pieces of the fundamental processes to add features observed to get towards reality, and each time we make some simplifications to advance process understanding, and then we have to put them all together, which is what we will do in the coming podcasts. Okay.